But today we kick off one of 2 weeks of stats, and most of you are going to have done some of this before, if not all. Hopefully it won't be too dull, but you'll be able to find out just how far we're going with it and what you need to know. Firstly, definitions. We're not a big definitions course. We don't write essays on definitions of things. We've got resource sheets, and we're not asking you to memorise things like that. But when we refer to data, it's just the results of an experiment. It's the scores, it's the ages, it's whatever you're collecting. We just call it, here's my data, here's my numbers. It's the information I've collected. When we talk about statistics, that's what I've done to it. Like, I've converted all those numbers into a statistic to say, the average age in this room is 18 and 1 month. Well, that would be a statistic that came from me asking everyone their age. So, stats is the outcome of analysing our data. So there's 4 main principles in stats, and a lot of you will be unable to avoid stats, and some of you might like it, I don't. But in first year, a lot of courses require you to do either Stat 1020 or Stat 1070, and it will go into designing studies and collecting data. All we look at here is the next 2. Presenting and analysing data and interpreting the results. So the first half you'll see, it's looking at graphs that someone's already made for you and asking you questions about. We've got some examples in the lecture, and most of that will be mostly common sense and just reading it properly. Just slowing down and go, yeah, I've read the question properly. As for interpreting the results, well, we'll get onto mode, mean, median and standard deviation soon to make sense of them. Now, types of data. This is something that will get done in undergrad stats, and they like to categorise the data into certain definitions. Firstly, population data versus sample data is not an issue this week. We'll talk about it next week, where we'll say population data is if I've got all the results. If I wanted to talk about Newcastle Uni students, I would want an answer from every Newcastle Uni student. But normally I'd use sample data, which is maybe I would sample this room and say, yeah, Uni of Newcastle students think this way. It wouldn't necessarily be accurate because you're a sample of the uni, but there's that difference. This week we're just talking about population data, no catches. We're just pretending we've got all the data for everything we do this week. Next week we'll look at the difference. So within just data, 2 types of data. First is qualitative, which is like, there's an example, I'm collecting data of people's favourite type of pet maybe. Qualitative is when the category is a word, okay? I'm not asking you how high you are, how tall, what age. It's not a number answer you give me. I'm asking you what type of pet you have, or maybe your favourite type, and you might say dog. That's qualitative, okay? That is just a word descriptor, not a number. And then if I did all that data collection and asked everyone their favourite type of pet, I could put it into a table that looks like that. And hopefully that makes sense. We call it a frequency distribution table. Fancy name, all it is saying, how are the frequencies distributed? In other words, 28 people here said cat, 42 said dog, and so on. So we call this a frequency column, frequency just meaning how many times did it happen. And we've given this table, this column, the X header, and sometimes we'll just call it score, outcome, result. It's just naturally labelled X, which is whatever question was you're asking. I was asking type of pet, that's the first column, and we just call it the X column. And then how many of each one happen. So qualitative, and the other ones are quantitative. Just think quantitative as in they're a quantity. Now, I'm not just saying quantitative ones have numbers in them. They've all got numbers in them. But the quantitative answers are numbers. So it might be a question I walk up and ask everyone, how many pets are in your house? That's a quantitative bit of data because the answer is a number. If I said, what pet? Qualitative, they're words. How many pets? Quantitative, it's a quantity. And then still, that would collect into a table that maybe 13 people said they had 4 pets in the house. 22 people said they had 5 pets in the house. Whatever the question was, the answer 4 happened from 13 people, and so on. So there's our 2 basic types of data. Qualitative words, quantitative numbers in the categories. Now a further split. Both of them have a two-way split. And this is examinable, as in this isn't just background, it's not nil watching. We'll get asked, what type of data is this? In qualitative, as in the word stuff, it could be nominal or it could be ordinal. Nominal means there's no natural order. I just focus on the NO of nominal. There's no natural order to whatever word categories you've got, like dog, cat, bird, fish, cow, ferret, frog. I could think up orders. I could say, what about alphabetical order? Or what about size of them? But it depends how big. There's no natural order to those words. Ordinal means there is a natural order, a very obvious order. Small, medium, large. They're very obviously ordered. Okay? So it's very obvious. If data is ordinal, it's a very clear order. It's not alphabetical. It's not maybe this. It's like low, medium, high setting on a fan. Low, medium and high are ordinal. There's a natural order. Colours, if I survey colour, hair colours, there's no natural order to hair colours. In the quantitative ones, we don't have nominal and ordinal because they're not words that describe stuff. They're just numbers. We either have discrete or continuous. Discrete means there's only a discrete number of answers you could get. As in, if I asked everyone, what's your age in years at the moment, as in just a round number of years, that would be discrete, because you'd either answer 17, 18, 19, 40 something. You'll just give that one answer. Continuous is when I ask you maybe how wide is your desk, and you might measure it and say it's 62.384796 millimetres. You could give me any answer there. In discrete data, you've only got certain answers you're going to give. Okay, they're numbers. It doesn't mean they have to be whole. Shoe sizes, 1, 1.5, 2, 2.5. That's still discrete. Discrete just means there's only certain answers that can be given. Continuous is when you can give any answer, any number in between. Okay? You could give 100 decimal places, you could give 1, but you've got an infinite number of options to give if it's continuous. Like a 1.75 shoe size doesn't exist that I know of. But in continuous, 1.75 exists, so does 1.8, so does everything. So there's the initial categories. We'll look at that more in the tutes. Now this is where we look at what are we going to get asked to analyse. There's the one I already looked at. There's a frequency distribution table. Here I've labelled it with a pet, but you'll still see it sometimes just labelled with an X. My categories are just X's. And frequencies, yep, they're F's. Okay, so X's and F's is a frequency distribution table. Now, from that data, we then want to make it visual. That table's good, but we might want to do any sort of graph. And we've got a stack of graphs. There's more beyond that, and we're not saying that you need to know what sort of data, do what with it. In stats in undergrad, they'll do that. They'll say, look, if you've got this sort of data, what should you do with it? We're not making you decide. We're just going to show you stuff and say, what's this telling me? Okay? Ask you a question about a graph that we've already made for you. Like that one. It's not well defined. Let's pretend that we walked up to people and said, what's your favourite type of pet? So there's the numbers we were discussing. A column graph. What's good about the column graph? It's just visual. Clearly, dog was the most common answer. But we can also get asked other things from it, like what percentage of responses were dog? Okay? What percentage of responses? If I'm asking what percent, that involves a total. Like dog, I can see 8 people said dog. If we're asking what percent, it means 8 out of how many? I definitely need to know that. And yes, I can find out from this, because 8 people said dog, 5 people said cat, 2 said bird, 3 fish, 2 rodent, 1 cow, 4 other. So if I add them to get 13, 15, 25, that's what fraction? 8 out of 25 people said dog. If it actually wanted percent, remember any fraction or decimal times 100 becomes a percent. In other words, if I just times that top and bottom, I can see that's a 32 on 100 times 100. We got calcs, don't need to go there. 32% of people in this survey said dog. So again, hopefully that's a common sense thing. I can get the 8 from the graph and I can get the total from the graph by adding them up. What other type? A horizontal bar graph. Okay, if the names are long, it sounds like a pretty silly way to choose a different type, but as a column graph, that'll be hard to read. So there's just a horizontal bar graph. A dot chart. It's not really any different from that horizontal bar chart. It's just instead of doing long bars, they're just showing the dot. Okay, so that's some old data about teenage birth rates. I could still find out a lot of things there. That, okay, in 1970, Iceland had this 70-something% teenage birth rate, whereas in 1998, they only had 20-something%, and so on. So we could get asked questions on that. Another one, a divided bar chart. All these are, in order to get described in the question, is there's all the numbers. Hopefully they add up to 100, 53, and a 38, and an 8 and a 1. There's 100% of all data. The only thing that's visual about it is 53% of the bar chart is taken up with the blue. 38% of it is Hindu, and so on. So it's a nice visual representation. So we could get asked that question. Given that the population of Fiji is 900,000, how many Fijians are Muslim? Okay, well, all I need is, this is Fiji's percentages. I'm discussing 8% of the population, and the population is 900,000. So all I've got to remember here is, how do I work out 8% of 900,000? And of the times, 8% of that. Again, I'm not going to bother to go through and do it manually, but if you went to the calc, just 8 on 100 is fairly simple. Do that times 900,000, and then it will give us that's 72 and 3 zeros from the calculator. So yep, I can work out from these charts. There's another type, a pictograph. Not great stats. That's actually a really bad graph, or it's deceptive. But this is the sort of thing we see in newspapers all the time. It's not inaccurate, but this to me says, okay, we're talking about new residential construction, and here I'm looking at this, housing completions. Well, in August 2001 they were here, by September here, in September 2000 they were here. It looks like a huge increase, but it's not going down to zero. If my axes went from 0 to 1.6 million, the tops would be almost exactly the same. But anyway, they're pictographs, and it's still real data. It just looks a bit deceptive. This one's worse, but this is a pictograph. And this is a common one sort of used in newspapers to say, okay, category A had this level, category B had this level. In this example, we're saying category A, whatever, had an average of 1, and category B had an average of 3. But the problem with that picture is B looks more than 3 times bigger than A. But you look at that, I can fit 9 of those little size picture inside of the big size picture. So whereas you could say, look, they're not lying, the picture's lying a bit, because this picture is 9 times bigger than that little picture, and makes it look like this massive thing, when really it's only 3 times. There's a nice accurate one. If you're going to do a pictograph, A was 1, B is 3, that's fair. That one's a bit unfair up top. Again, this is background because we're not constructing them. We're giving you graphs and asking you questions. Pie chart, really common. We've seen pie charts before. We might get asked, once again, not to construct it. You don't need a protractor, you know, measure out the degrees and all that. But you need to know how they're constructed. Like, here's a question. How many degrees of the circle does refrigeration segment occupy? So I can see refrigeration is 8%. How many degrees in the entire circle? We're putting that in as assumed knowledge, but 360. Do a full 360, you're back where you started. So this question is really only asking me, if I was going to do it manually, how many degrees of the circle would be 8%? Well, it's asking me what's 8% of 360. And then, well, I'm just going to, without the calc at the moment, simplify it a bit. 36, let's halve that and halve that. And we've got a 80 on 5, 2. I have a calculator. Why do it the hard way? 0.08 times 360. Okay, 28.8 degrees. But yet, if we can find percents of things, we've introduced nothing new. What other sorts of graphs might we get chucked? A line graph, pretty predictable. We've seen these before, and okay, it's January through to December, so it's mean monthly rainfall. We'll talk about mean soon, just meaning average. Clearly Perth looks pretty dry in the summer, wet in the winter. Melbourne is pretty consistent, and Newcastle's subtropical, drier in the summer, wetter in the winter. Where's a question for that? Which is the wettest month for Newcastle? Fine. All we've got to know is Newcastle's the blue line, okay? The wettest month, not driest, so clearly I'm looking for a top level, and the highest blue point right there. So all we need to say it's March. March is clearly the wettest month for Newcastle. Okay. This one, a radar chart, I'm not a big fan of it. Uni uses them all the time. In our performance, when we get you to do your surveys and say how things are going, they always give us results in one of these. And it's a way to about easily compare. Like here I can look at January and look at the actual numbers. It's harder to find actual numbers over here because I've got to say, oh look, 40 is meant to be this line. So 40 is that line, that line, that line, that line, that line, that line. So they're not very easy to read in terms of what's the actual result. But in terms of trends and that, okay, it's pretty good. I can see that in January, clearly Sydney is the hottest, then Bermuda, then Memphis is the lowest. We've got a 0 in the middle and 100 out there. And we do a swap around where Sydney is coldest, Memphis is hottest, and so on. Okay, so radar charts will happen. I think we've got one in this week's sheet. Here's one just grabbed to make sure we're reading the graph properly. Again, there's no real deliberate traps, it's just reading it properly. How many female employees were there in 1994? So instantly it said female, so I only care about the light pink. It said 1994, so this is clearly what it's referring to, and we're up to 100. Okay, I'll just check that I read it right. 100 female employees in 94, all good. How many employees did the company have in 96? It's segregating 96, but it didn't say female. So I could fall in the trap of thinking, oh, it's just this again. Now, I know this isn't a great graph. It's like, well, God, is that halfway or not? Halfway will do, okay? We can see that, let's assume that this is halfway. But it said how many employees. So I've got to say in 1996, there were 200 male, and that's 150, that's 200. Halfway in between would be 175. So I better answer that with the 375. So 200 plus the 175 to give me total male or female employees. How many more males than females were employed in 95? They're saying, firstly, that there were more males than females. That's true. Light pink is less than dark pink. And how many more means what's the gap? So we had 175 males and we had 100 females. So how many more? There were 75 more male employees than female employees in 95. So the numbers aren't bad, it's just reading it properly and safely and maybe slowly at times. Okay, got some more of these. Another. Tasmanian apple production. It's got a legend on it. The legend on the previous one was just male versus female. This legend gives us extra info, so we've got to read everything available to us. And notice that it says in thousands of cartons. That's what this means. So if I've got an answer, if I look at this number here and say 500, 400, 300, 200, 100, this answer here, say, that looks like the answer is 100, it's not really 100, it's 100,000 cartons. Because my legend tells me that this is measuring in how many 100,000 cartons. So if the graph tells me 100, it's 100,000 cartons. So for which varieties was there an increase in production from 95 to 96? So from light pink to dark pink, where did it get bigger? Light pink to dark pink went bigger. Light to dark, nope, light to dark. Light to dark got bigger. Nope, nope, nope. Okay, only 3 categories there satisfied the question. They got increased from 95 to 96, and that was the Golden Delicious, the Red Fuji, and the others category, where others were just all grouped together. In which variety was there the biggest decrease? And from 95 to 96, so decrease, well, surely it's going to be this one. That's a pretty big decrease. That's a moderate decrease, but it's clearly not as big. This is like 1.5 of these categories. That's about 1 of the categories. Nothing else has anything like it. Definitely the biggest decrease was in Red Delicious. I don't have to measure it. Didn't ask me that. It just said which was the biggest decrease. Absolutely, from light pink to dark pink went down the most in Red Delicious. Now, how many Granny Smith apples were produced in 95? This is where it's, you could call it a trap. It's making sure we quote this. So Granny Smith apples in 1995. Granny Smith 95 is light pink. And I've got to do a bit of estimating here. If that's 200 and that's 300, I might call it 220. Within this semester in applied, sometimes it won't be perfectly accurate. And you'll say, oh no, it's 210, it's 220, I can't quite tell. That's fine. As long as you're getting something like this, but you finish it off with 220, but it's 1,000 cartons. Not 220 apples, not 220,000 apples, 220,000 cartons of apple. So just, it's like reminding us to put our units on there, but the units were in the legend. Okay, what other ones? Okay, this is where I stuck it, not in the worksheet. What's the average rainfall in January for Melbourne? So it's an average monthly rainfall for Sydney and Melbourne, and the question's asking for January and Melbourne. January, Melbourne, that's the one I'm trying to work out its value. And like I said, it's not always easy working it out, but that 40 is meant to align with this radar line. That 60 aligns with this. As you can see, the 140 aligns with this, and the 20 aligns with this, and the naught is a centre. So when I'm looking at this, I can see that that's the 40 line, and that's the 60 line. 50 will be about there, so it's about 45. That would be a totally good enough estimate. If someone put from 43 to 48 there, great. What's the average rainfall for January in Melbourne? My stuff up there. I renewed the numbers, but what didn't I do? Forgot to write the units on there. Okay, so really these things should have a units, and I forgot to put units in the question. So all those numbers in the header should have said average monthly rainfall in brackets millimetres. So 45 millimetres. What's the driest month of the year in Sydney? Now we've just got to stop and check. Does that mean I want large numbers or small numbers? But since it's rainfall, yep, I want small. I want Sydney. Where is the Sydney red line closer to the centre dot? Well, the red line closest to the centre dot, here it is on the 80 line, here it is going under. That's my favourite at the moment. Now it's going out. That's definitely it. That's the closest it gets to the centre. Okay, it's the only one that comes way in from the 80 line. The 60 line is the next one. So here's 60 line and here's the 80 line. I'm going to go right on 70. Oh, it didn't even ask. What's the driest month of the year? I don't have to measure it accurately. All I've got to do is read the question, which I didn't. September definitely has the smallest rainfall for Sydney in the year. Okay. Again, I almost screwed up. I wanted to write 70 millimetres. No, read the question, that's all. Here again, this is what I was talking about with pie charts. Don't want you to get protractors, just want you to understand the concept of you've only got 360 degrees to play with, so however much each category takes up a relevant, a proportionate amount of degrees. So here is my answers to my survey. It was a qualitative survey. People answered me with words. They answered me with car, motorbike, bike, train, bus or walk for how they got to uni. Okay, let's say it's the main one. They didn't give multiple answers, they had to give one answer, my main method of getting to uni, and this is what happened. So there's 1, 2, 3, 4, 5, there's only 6 different categories, but it's not only 6 people I asked. 6 people said car, 4 said motorbike, 2 said that, and so on. So really, how many people did I survey here? There's 10, 12, 15, 16, 17. I surveyed 18 people. There's 18 answers in this table, 6 unique answers, but 18 people were surveyed. Now the fraction, that fraction just means the fraction of, what fraction of people said car? 6 out of 18. My fractions are all just going to be divided by the total of 18. So I've got 4 out of 18 said this, 2 out of 18, 3 out of 18, 2 out of 18 and 1 out of 18. And I know that if I added all of them up, I'd get 18 out of 18. In other words, the number 1. But I know the fraction of the circle, how many degrees, considering that there's 360 degrees in total. I just want to go to the calculator and work out what is 6/18 of 360 degrees. Okay, and it will come up with, it's a third of that, 120 degrees. Don't worry about the calculator stuff. It'll effectively be, that'll be that, that'll be that, that'll be that. If I add all them up, I get 200 degrees plus another 100 is 300 plus 360. Okay. As long as we knew how to construct it, all I needed to know was the fraction. It could have asked me for what percent. Well, if they did, I would just get 6/18 times 100 and make it a percent. Same old issue, fraction or decimal to become a percent, just times by 100. And then the bit that we don't need to bother about is, that's 120 degrees, okay? 90 degrees will be about here, so that's 120. 80 degrees for the motorbike, 40 for the bike, 60 for the train, 40 for the bus, and 20 for walk. But if we could fill in a table like that, we're sorted. The pie charts are sorted. Okay. Here's a pie chart of nearly totally accurate numbers. I adjusted them a slight bit just to make it easier to calculate. What percentage of the offers? This is for 2014, and we had, well, 90 offers for primary teaching and early childhood, 85 for arts, 35 offers for nursing, and all of that. Other, that's pretty normal now. We used to have 30% going to primary schools, 30% going to nursing, but now our other category, we're doing all sorts of stuff. But it's not what we're here for. What percentage of the offers were for nursing? Well, clearly nursing is 35, and I either need to add up all these numbers to find out the total, or even easier, it was in the total. It was in the title, the total was. So what percentage of the offers? Well, 35 out of 500 were for nursing, okay? In my head I'm thinking that's the same as 70 on 1,000, which is the same as 7 on 100. Either way, the calculator will spit that out as 7%. A 35 on a 500, or I could have cancelled, times 100, 7% of the offers. That's about as hard as our pie charts get. So that's it for those. They were all qualitative data. They were all categories that had words. What if the categories are numbers and they're quantitative? Okay, these categories are just temperatures in degrees Celsius. Maybe these are temperatures over however many days in Darwin or something. And each dot just represents a day where it hit that temperature. So on 4 days, maybe it was 38, 2 days it was 39, they had one freak day at 42. But there's a dot plot just laying out the numbers. Here's another way we could do it. With a frequency histogram, it's still very much like a dot plot. It's like a dot plot, but if I drew rectangles, I'll suddenly call it a frequency histogram like this one. Instead of dots at the top, they're columns. No real big difference. Notice that frequency histogram has been converted to this. Distribution table has been converted to this. Now note that it's always f is the y-axis title, and x is still where we're used to x being. Okay? Another reason we call the categories the x-axis, or call it x, is because it is always our x-axis. So anything that changes between here and previous is it's not a y-axis, it's frequency. So this tells me that a score of 1 happened 4 times. Yep, that's a miss. A score of 2 happened 9 times, so 2 went up to 9. 3 happened 6 times, 4 happened 7, 5 happened 3, and 6 happened once. Yep, perfectly formed into a frequency histogram. Now, frequency histograms and polygons are the only ones we're going to get you to construct. Okay? But it's pretty minor, and will give axes, grid, labels. Okay? So this overhead is basically saying, yeah, it would request this, but would give you this thing here, which makes life easier. So I've got x's of 5, 10, so yeah, all of these things. 5 happened 4 times. So initially I normally just mark the dots, crosses, whatever. 5 happened a frequency of 4, correct. 10 happened a frequency of 5 times, there it is. 15 happened 7 times. 20 happened 3 times. 25 happened once. And 30 happened twice. Okay, there's the guts of my working out done. But we just got told, and we'll see, some of us might be tempted to join the dots. In a second we'll call that a frequency polygon. But frequency histograms, as is shown on the last page, are these box things. That's what a frequency histogram is. And the way you draw the boxes is, consider that dot to be halfway in the middle. Okay? So each dot you put is halfway in the middle. These things meet. They share walls. There's no gaps between the columns. They share walls, and the dot is slap bang in the middle of the column. In some things, that column might represent everything from, say, 12.5 to 17.5. Okay, it might not have been a whole number of answers, and anything that landed between here and here, they just put in this column. That's why the column goes perfectly around the centre of the mark. The mark was 15, the column straddled it. That's a frequency histogram. So if we can draw rectangles like that, awesome. But I did mention a frequency polygon. And all the frequency polygon, basically, with a but, it basically is the same thing, but join the dots. Look at that one. 1 happened 4 times, so there's a 1 there. 2 happened 9 times, 3, 6, 4, 7 times, 5, 3 times, and 6 happened once. The only thing that I've done apart from join the dots is at the start and at the finish, polygons come back to the axes to say there were no scores of 7 and there were no scores of 0. Okay, so these polygons might just be join the dots, but wherever they end up at the ends, drag them back to the axes at what would have been the next value and the previous value. So really this stopped here, but take it to a 0 on the next value. Really it's only started here, so take it to a 0 on the next one back. Easier to see it constructed. Again, incredibly predictable question for us. We've just got to know, a resource sheet will do, a polygon is the joining the dots things. A frequency histogram is the boxes. That's it. So I'll still start them off exactly the same way. 5 happened 4 times there. 10 happened 5 times. 15 happened 7 times. 20 happened 3 times. 25 once. And 30 happened twice. But instead of drawing boxes, all I'm going to do is join these dots. Join. Join. Yep. Yep. And the only other ones is, don't just take it back to the axis like vertical or just a random point. At what would have been the next point, which is this one, take it to 0. What would have been the previous point, yoink, 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 this one, the polygons start and finish at 0. That's the extent of our graphing for the week. Pre-provided grid, labelled axes, and more often than not, we might say, draw a frequency polygon and histogram on the same graph. Well, if that happens, that's fine. We just, oops, no, not arrow. Where's my colour? So if someone asks for frequency polygon and histogram, I'm not going to bother drawing on two separate ones. I would just have done the same thing. Here's my histogram forming on the same axis. I know we already have done this. And I will just make sure I let the marker know, however, that that's my frequency histogram and the other is my frequency polygon. That's them. Okay. Once again, this is just another way data can be represented, having the males here and the females here, and we could go through and analyse that, okay, there's this many of this, and we've got different years. I don't think I've got a question on that. Now, going on with what we just did, actually I should say on this one, really that was, we call it a histogram there. It is like my columns there. It's just turned on its side, back to back. Notice that this is, what is it, estimated residential population and projected population. So the population in 2006, what they expect in 2026. So in females, the distribution in 2006 was sort of like that. So if I'm trying to picture that this way, it's not perfectly symmetrical. Okay, I can see we expect clearly a smaller population of 80-odd-year-olds than we do of the 40-odd-year-olds and the youth. And here, well, this one drops off sooner because it's the men not lasting as long. So, okay, there's still data that can be gotten out of that. But this is my simplistic view of it. When we talk about data, we talk about its shape. And once again, I've taken off a side, we're just looking at it. This is symmetrical. This is saying, like, whatever the survey was. Maybe this would be a survey of heights in this room. I don't know, what's the average height in this room? 1.7 metres. I don't know. So most people were that height. We had a good number of people at 1.6, good number of people at 1.8. We had very few at 1.5 and very few at 1.9. That would be some sort of symmetrical distribution. Rightio. What might really happen is it's left or right skewed. Now those definitions can seem a bit backwards. Like if I'm looking at this saying this is left or negatively skewed. Firstly, why is left and negative associated? Just think of the number line. There's -1, there's -2, there's 1, there's 2. The negative numbers are on the left. That's negatively skewed. The positive numbers on the right, that's positively skewed. But why do we call, when the bump is on the right, we call it left skewed? Well, think of it, and this will sound pretty juvenile. That's a whale. Where's its tail? And statisticians will talk about where is the tail of the data. As in, if this stuff wasn't there, just say these low results didn't happen, I would have said that was pretty symmetrical. But it's the tail that caused it to be skewed. Okay, so that's pretty symmetrical. The tail is what we're discussing, this issue, and we call it left skewed or negatively skewed because that's where the tail is. Okay, so the tail of the data is on the left here, and the tail of the data is on the right here. Another way I've heard someone liking to think of it is go up to the middle one. If you push that with the right hand, it will end up looking, I can't do this in reverse. If I push that with the right hand, it looks like that. So that is right skewed because it looks like it got pushed with the right hand. That one got pushed with the left hand. Personally, I prefer just doing the whale because where is its tail? And that can mean a lot to us, okay? Maybe not where to get heavy into this, but in stats in undergrad, you need to know if there's a skew, as in it's not symmetrical, is it left or right? Also in shape of a distribution. Unimodal, and we'll talk about the word mode soon, means there's one peak. the mode we're going to refer to as it was the most popular answer that happened. Okay, so this one here is unimodal, it's bimodal because there's two peaks, and that's multimodal. So of course we could get any sort of variation there, and that could be really relevant to us if there's one peak or two peaks or whatever. So unimodal, bimodal or multimodal, and the other things was left skewed, right skewed or symmetrical. So we use all of these things to summarise the data. If we've got a table or a spreadsheet full of numbers, it's really not much use to us. But the two main ways to describe data are measures of central tendency, which describes where the centre of the data is, or measures of dispersion, which talks about how varied the data is. So in this one, if I was looking at this bit of data, and I had lots of these results, not many of these, not many of these, its centre is right there. If that was 2 and that was 10 in whatever readings I was looking at, then maybe that's 6. The centre of the data was at 6. Doesn't tell me anything about how spread it was, because here's another one where its centre of data is at 6. Notice both of them have the same centre. Maybe they were blades of grass and I measured them all in this certain area. The average was 6 centimetres is the length of blades of grass. So the measures of central tendency gave us 6 for both of them, but we're going to use measures of dispersion later to say, yeah, but were they, most of them, bigger than 6, smaller than 6, or really close to 6? So firstly, we're just going to look at central tendency and we'll get back to measures of dispersion. How spread the results were, not yet, just measures in the middle. And you won't have avoided these terms before, mode, mean and median. And we'll just confirm what each one means. Now, mode is a nice, very clean-cut one, as in maybe not as useful as some of the others, but mode just occurs most frequently. I've always sort of the mode, the MO, mode happened most, fine. So in that data, a very simple set of data, 2, 3, 4, 4, 5, 7, 9, clearly the mode is 4. It happened more than anything else. I got 2 4s, but one of everything else, the mode is 4. In that set of data, 4, 4, 5, 6, 7, 7, 7. 4s happen more than 5 and 6. Is that a stretch, Ruth, or a question? Okay, enjoy. But 7 is the mode. Again, it's which one beats all of them. There are 3 7s and nothing else has 3 of them. Mode 7. If 2 observations occur the same number of times, and more frequently the other, the distribution is bimodal. Meaning, okay, first thing I would do here is write it in order. 2, 4, 4, 5, 7, 8, 8. It's not a have to, it's just to make sure I don't miss it. Because initially it looked like the mode was 4. But I've got 2 4s and 2 8s. The mode was 4 and 8. Okay? If they're both equally as high, they're both modes, 4 and 8. What if it's 1, 2, 4, 5, 9? No mode. No result occurs more than any other result. There's no peak. There's no mode. What if it was 1, 1, 2, 2, 4, 4, 5, 5, 9, 9? It's all the same, but everything happened twice. Did any result happen more than any other? There's still no mode. I don't care that they've all happened twice. No one answer stood out above the rest. Nope, no mode. That example there, 2, 2, 4, 4, 7, 7, no mode. Okay? If I then stuck a 9, what's the mode now for this set of data? The 2, the 4 and the 7, because they all happen more than the 9 does. There are 3 peaks, trimodal. So, and here's the way we'll assess it. Find the mode of the following data. The first lot, again, I'm trying to trap, and just trap for the 4 answer only, but put it in order. It's a 2, 2, 3, 4, 4, 7, 9. And again, 2s and 4s. The mode of this data is 2 and 4. They both occurred more than anything else. In the next one, Same thing happening. I just need to check my order. 11, 12, 13, 14, 16, 36. There were no other similar ones. I had no mode there. What's the mode of the last one, you reckon? There's two main answers that will come from answering this question. The two answers I think that will happen is the answer of 2 or the answer of 18. Is anyone a fan of each? One of those is correct. Which one's correct? The 2. It's true that we go to the highest frequency, but the answer's not 18. What happened 18 times? 2. There were more 2s than anything else. There were 5 zeros, 13 1s, 18 2s. So the highest frequency tells us that the mode was 2. Okay? All right, let's put a 10-minute break there. Okay, so the mode was just the most frequently occurring. Fine. The mean, same as average, okay? There's no actual difference between, except for spelling. The mean and the average are the same thing. You may have seen it around before, but it went down well. So, average is just mean represented by. We've got something missing there. It should say represented by an X with a bar on top of it. So X we said, X represents scores, okay? If you've got all your scores, they're all just your X's. That bar on the top just means the mean of all your scores, or the average of all your scores. And it gets called X bar. Okay? X with a bar on top. X bar. And we know to calculate the average, all you do is sum up all the observations, add up all your numbers, divide by how many numbers you've got. So, same old sort of notation we've done before. Oh, it happened, came back. And X bar, now this, we've had this definition before. Sum of all your scores over the number of scores. Stick with it, that's totally fine. This is just another way of seeing it. You'll see in maths sometimes this capital sigma, it just means sum. So that's saying your mean is equal to the sum of all your X's over the number of scores you have. You don't have to go with the fancy notation, but we're going to use it again today. So that just means sum them up. Sum up all your scores and divide them by how many you've got. Rightio. So if I had to find the mean of that data, I don't care about putting them in order this time. I cared when it was mode. I don't care this time. I just add them up and divide by however many I've got. I've got 1, 2, 3, 4, 5, 6, 7 scores. They add up to 5, 8, 11, 16, 17, 18, 19, 20, 21. So my mean here is 21 on 7. A mean of 3, that looks about right for numbers ranging 1, 2, 3, 4, 5. There's my mean. For those ones there, nothing different. My mean is equal to 1, 2, 3, there's only 6 scores. If I add them up, I've got 52, 65, 67, 77, 91, 92, 102. And it may end up pretty, it may not. If I do that, it's 17. So, mean of 3, mean of 17, there's nothing new here. This one's different. Now, here's a frequency distribution table with something else added into it, which you need to look at. The first thing just said X meant the scores and F meant the frequency. So really, the data I've got here, 0 happened 5 times. 0, 0, 0, 0, 0. And then 1 happened 13 times, etc. 2 happened 18 times, and so on. So I've really got lots of data here. In actual fact, if I sum up the F column, the sum of this F column is 50. There's 50 scores in this table. It would be tempting to think, hang on, 1, 2, 3, aren't there only 6 scores? No, because there's lots of each one. Okay, so there's 50 scores. We know to find the mean, we have to add up all the scores and then divide by how many scores there were. So automatically I know my mean is something over 50. Not over 6, there's 50 scores. But how do I add them all up? Well, I could go through manually and say, what's 0 plus 0 plus 0 plus 0 plus 0 plus 1 plus 1 plus 1, 13 times. All this fx column is doing is helping us. The fx literally means f times x. So if I've got 0 5 times, the sum of all those noughts is 0 times 5, which is 0. If I want to sum up 13 ones, they're going to add up to 13, 1 by 13. If I want to add up 18 twos, they're going to add up to give 2 lots of 18, which is 36. So all the fx column does, and all we ever use it for, is to help us find the mean. So fx is only for the mean. If requested for the mean from one of these tables, the fx column helps us. Doing it manually will just take ages. So if they're all my fx results, in other words, all it was this column times this column. It doesn't matter whether you think that times that or that times that. X and F, F and X, same thing. They all multiply to give that, and the sum of all of that column The sum of the fx column is the sum of all the scores you've got. That goes on top, and the 50 goes on bottom. So you'll see a formula for mean that says the mean is equal to the sum of fx over the sum of f. It looks horrible, but all it's saying is the sum of fx is the sum of all the scores, and the sum of f is how many scores. So that horrid-looking formula is just exactly the same as sum of all scores over number of scores. There's nothing wrong with the answer 96 on 50, but you could change it to a decimal if you wanted, and it would be 1.92. And so there's the mean of that data. So on the whole, it's pretty simple. Just I would note that if you get given in a table, it's always the sum of this one over sum of this one. So some examples for us manually. 2, 3, 3, 4, 8. No traps. I've got 5 numbers. The mean, the sum of them, I've got 5, 8, 12, 20. The mean is 4. All good. Then I check my answer and go, yep, 4 looks about right. If I stuffed up somehow and got 14, it can't be. A mean has always got to be in the middle of all these numbers. It's not going to be some extreme number. Find the mean of these scores. Note there's a column left unlabelled and all that, but that's just saying we've left that there for you to do an fx column, because fx will help you add all these up. Now I already know what's the main incorrect answer for this question is saying, well, 1 plus 2 plus 3 plus 4 plus 5, that all adds up to 15. And there are 5 scores. 15 on 5 equals 3. The mean is 3. If the only scores we had were 1, 2, 3, 4 and 5, you'd be right. But it's just not true. I've got 4 of them and 9 of them. You can't ignore the F column and just go for it. We need the FX column to help us. And I also want to sum up the F column, because if I've got 4 of them and 9 of them, let's add this up. 13, 19, 26, 28. I'll just check that again. 18, 28. Yep. So the sum of the F column is actually 28. Let's make the FX column. 4 ones is worth 4. 9 twos is 18. 6 threes is also 18. 7 fours is 28. And 2 fives is 10. So I add up all of that column. We've got 28, 38, 48, 58, 66, 74, 78. So my mean is, I'm going to write this even though I don't have to. It's the sum of the FX column over the sum of the F column. It's my 78 or my 28. Get the feeling that's not going to be as pretty as some of the others. 78 divided by 28. Yeah, it's a bit horrid. It goes on with lots of decimal places. 2.78. 2.8 to 1 dp. That'll do fine. It was a 2.78. I rounded it up. An average of about 2.8. And I rounded it, so I just wrote 1 decimal place, 1 dp. Okay. So we've done mode, we've done mean. The median, okay. I was thinking like the median strip in the middle of the road. It's just in the centre, okay? Now, they're all meant to have something to do with the centre, but the median is the middle value in an ordered sequence of data. So literally, if I put all my numbers in line and work my way into the centre, that centre one is the median. So we go in order from smallest to largest, and well, we'll look at the next definition in a sec. 1, 4, 3, 3, 5, 3, 2. So the first step is put them in order. Don't just count your way in the middle. It's meaningless unless they're in order. So if I put them in order, I'm going 1, 2, 3, 3, 3, 4, 5. 1, 2, 3, 3, 3, 4, 5. Yep, got them all. There's not many numbers here, so I could just totally just do this manually. There's the ends, there's the ends, there's the ends. Clearly what's in the middle is a 3. Done. Median. The median of the data is 3. It won't always happen so nicely. Let's check this example. Are they in order? Nope. 11, 12, 13, 14, a 16 and a 37. All right, let's swipe the ends, wipe the ends. If I've got 2 in the middle, the median is just halfway between them. Okay? I don't quote 13 and 14 like I did with mode. The median number is just in the very middle of all this data. In the middle of a 13 and a 14 is my answer of 13.5, 13.5, whatever you want to call it. And if you're ever trying to find the middle of 2 numbers and it's a bit hard, like it might be a 13 and a 28, remember, find the middle of the numbers just by adding them and dividing by 2. So straightforward here, but I could have added 13, 14, gone 27 on 2. Yeah, that's 13.5. So technically it's the average of the 2 middle numbers. So there's a trend we're going to see happen and talk about a bit more. 1, 2, 3, 4, 5, 6, 7. When there are 7 numbers, there is 1 in the center. Yeah? RE. 1, 2, 3, 4, 5. If there are 6 numbers, note there's 2 in the center. So it's different. Every time you've got an odd set of numbers, like my 5 fingers, there's only 1 central number if you've got an odd set of numbers. But if you've got an even set of numbers like 10 figures, there are actually 2 in the center that you've got to find an average. So let's just do them manually first. The only trap here is, no, the median is not 2, because they're not in order. 2, 2, 3, 6, 7. Clearly the 3's in the middle, that's the median. The next set of data. 3, 4, 4, 6, 6, 8. 3, 4, 4, 6, 6, 8. Yep. The middle, well, it's actually here, so I've got to find the average of these 2. Or halfway between a 4 and a 6. Yeah, it's a 5. So I've got a median of 3 and a median of 5. Nice. But what about when you've got lots of numbers? This is me doing the finger thing again to say, if you've got an odd set of numbers, so in 5 numbers, I want the third. An easy way to find that, because maybe it's an odd set of numbers, like if I've got 67 numbers and I want to know which score is in the middle. Think of what happened here. 5 numbers, I can think 5 plus 1, that's 6, and 6 on 2 is 3. That's all this formula is saying. This is saying if you've got an odd set of numbers, this may help you find the middle. If there's 5 scores, think of what's 5, plus 1 is 6 on 2, it's the third score you want. That's all this little formula is doing, okay? It's saying add 1 and then halve it. So for 5 scores, I want the third. For an even number, I know for 10, I want the 5th and 6th. So if you've got an even number of scores, I want to find half of this number and the next one. And so I know that looks horrible, but it says find the mean of the n on 2th, that's like 10 on 2, find the mean of the 5th, and n on 2 plus 1 is just the next one. So say, for example, what if I had, the example I just mentioned, what if I had 67 numbers? Well, 67 plus 1 is 68, and on 2 is equal to 34th. If I lined up 67 numbers and I was asked for the median, I just want to know what the 34th score is. That's it. What if I had 120 numbers? Well, that's even. I'd want to know the halfway mark, the 60th, and also the next one. So the even ones are easier in that way. Halve the number and give us the next one. I'm not saying the median is 60.5. Depends what the 60th score is and what the 61st score is. But we need to find them. So let's try this. Here's lots of numbers. So there's 50 numbers here. Again, I can understand an easy trap to say, well, what's the median? We've only got these scores, so that's gone, that's gone. The median must be 2.5. But I'm totally wrong, because it's not one of each score. If there's one of each score, fine, the median is 2.5, but it's not. So what we do here is, well, I know that if I've got 50 scores, I want to know what's the 25th score and what's the 26th score. And I don't really want to write them all out. The only other column we're going to discuss today is a CF column, which is a cumulative frequency column. So that's the F column. But the cumulative frequency column is when we say, sure, I've got 5 scores to start with, so I just write that number here. But then I've got 13 more scores, and 5 plus 13 is 18. So far I've got 18 scores. Plus then I've got 18 more scores, which gives me a total of 36. So cumulative means you're adding up the total. How much do they accumulate? Add another 10, we're up to 46. Add another 3, we're at 49. And add another 1, we're at 50. No fluke this. They will always be the same. The total of the frequency column will be the last number in the CF column, because all the scores should have added up to 50 scores. Absolutely. So if they're ever different, you've just made a typo somewhere. But I haven't explained why. What's so useful about this cumulative frequency column? Me covering that on the screen doesn't help, but if you just looked at this row, basically that's saying up to the 5th score were all zeros. The 1st, 2nd, 3rd, 4th and 5th scores were all 0. Then this says up to the 18th scores were 1. In other words, after the 5, the 6th, 7th, 8th, 9th, 10th, 11th, blah, 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 onto the 18th were all 1s. But the 1s stopped at the 18th score. This row tells me that from the 19th score through to the 36th score, they were all 2s. From the 37th score to the 46th score, they were all 3s. From the 47th through to the 49th, they were all 4s. And the 50th score was a 5. But what do I care about? I said, to find the median score for this data, I want to know what's the 25th score, and I want to know what the 26th score is. If I look at this column as the one that interests me, because the 18th score stopped there, that tells me nothing about the 25th score. But the 19th scores all the way through to the 36th score were all 2s. They were both 2s. Okay? Everything after the 19th score up until the 36th scores were all 2. So that included the 25th and 26th. And what's halfway in the middle of a 2 and a 2? 2. So the median score for this data was just 2. Okay? Now let's do another. I know these are... Yeah, good. These are a pain. Now, again, we said before the FX column is for mean. The CF column is only for median. So if you're ever getting asked to maybe fill in a column, FX is only if we're discussing mean, which we're not in this question. The CF column is only if we're discussing median, which we are in this question. So I'm going to do a CF column. CF column was, how many have we got so far? Well, we got 6 scores so far. That's always the same as the F column. Plus 12 scores gives me 18 in total. Plus another 2 gives me 20. Plus 7 gives me 27. Plus another 7 gives me 34. Plus another 6 gives me 40. I'm just going to do a check over here. 6 plus 12 is 18, 19, 20, 27, 34. Yep. Everything's good. I've got 40 scores here. The last number in the CF column is 40, and my total of Fs was 40. If I've got 40 scores, that's an even number. We said for 40 scores, like 10, I wanted the 5th and the 6th. For 40, I want the 20th and the 21st. So I want to know what's the 20th score and what's the 21st score. What's the 20th score? The 20th score is a 14, and the 14 stopped there. So the 20th score is 14. What's the 21st score? The 20th score stopped at 14, so the 21st, 22nd, 23rd, all the way up to the 27th were all 15s. So my CF column just helped me do that quicker. It told me where the 20th score was, and I knew the next one after it was the next score. So my final answer is the average of those two. My median is the average of 14 and 15, which is slap bang in the middle of them. The median of all these scores is 14.5. And that looks pretty reasonable. Scores that range from 12 to 17. I've got a median of 14.5. Yeah, sure. Okay, so that was if there was 40 scores. But I assume, hopefully next, I've got one that's an odd number of scores. Okay? Let's check if I do. Let's find out. 12, 19, 22, 24, 25. Good boy. So there's 25 scores here. Which score am I going to want to find? I know with odd scores there's only one in the centre. And the trick was 25 plus 1 is 26. Halve it. All I care about is the 13th score. So I'll fill in a CF column, but all I really care about is I want to know what the 13th score is. 25 plus 1 is 26, halve it. The 13th score is my answer. CF column will help me find it. CF column always starts with the same. I've got 4 scores so far, plus 8 is 12, plus 7 is 19, plus 3 is 22, plus 2 is 24, plus 1 is 25. Good. I end up on the same number. That was me just doing that zigzag thing. The 12th score is a 4. After that is the 13th score. So it's like there's a line here. The 12th score is a 4, but after that, the 13th score, all the way to the 19th scores are all 5s. The 13th score is a 5. The median of this data is 5. Okay. I'll move quickly on from this, but it's still important to say, well, why do we care? Because we always use average, okay? Why do we have 3 different measures of central tendency? Sure, mean or average is the one we use mostly. Just gets them all, adds them up, and tells you where the middle of the data is. It's great, and we just use that, especially for evenly distributed data. If all your data is all like that, with heaps here, some here, some here, the average tells you the very middle, perfect. But what about mode? At what times could mode be more useful? Well, it's useful for nominal data. Like say we had all this data. An average here doesn't help. An average of that many Cokes, Diet Cokes, I can't average those words. It's a stupid concept. But what useful stuff could I get from this? The mode. But clearly this shop, the best interest here is not what's the average type of Coke sold, because that question doesn't even make sense. They want to know the mode, what's the most popular. So the most useful data here is the mode. Let's get more of them in. Another way, mode can be more than one value. If we've got some quiz results out of 5. Now, the mean will tell us that the mean result was about 2.5. What might be more useful to know is that we had a lot of 1s and a lot of 4s. And I agree. A mean of 2.5 to me makes it sound like most people got around 2.5. Not really. Most people got 1s or 4s. We've got a problem. Okay, people either got it or really didn't. That's like logs. We get that sort of data with logs. People normally either do well with logs or do really bad with logs. You either got it or you didn't. So modal data can be useful. And another one, here's like, look at this data. I know it's very simplistic, but if the data was 1, 1, 1, 5, 12, the average of those numbers, well, it's more useful here to say the mode. Sorry, this one in this case, sorry, the mode doesn't tell us anything about the centre. Because if I average those numbers, I might get something 5-ish. But here the mode is purely on one end. So sometimes if I said the mode of the data is 1 and said, okay, so the middle of the data is 1, no way. So the mode isn't very good in most situations, but it has its times to its use, mainly in sales. And median, I can understand why you think, why do we need a median? Why would I bother to stumble my way into the middle of data when all I've got to do is just find the average? Well, what's the first one? The median is at the middle of an ordered data set and therefore is only useful for ordinal variables. So if you've got variables that you can't put in order, the median is meaningless, because the very fact you're finding the median is I put them in order and then I found the middle. So ordinal variables, it's no use. But the main thing it's useful for is getting rid of extreme results. Look at this. 5 students in the mid-semester exam, not actual fact. 0, 62, 63, 67, 72. The average there, if I added all of them up and found the average, it would give me an answer of about 50%, 50-something. That's not useful. What's more useful is the median, which says the middle result was about that. And I would agree with that more. So the thing about median is you could have a huge result or a tiny result, and since all we do is step over it to get into the middle, we don't use that result. So the median is good when you've got some dodgy data at the ends, high or low. Okay? And as for mode, well, there's no mode there, so mode is of no use to that one. The mean was 53, the median is 63. There's one of the rare cases where median, that was more useful. Anyway, that's just the background. All we've got to polish off today with, we're on the N bit, is measures of dispersion. Now, and there's only two, one very simple one we'll look at first, range, and then standard deviation. Standard deviation isn't as bad as it sounds, and it sounds more impressive than it is. But firstly, let's look at these different sample groups. Whatever these readings are, in sample 1 they got readings of 6, 7, 10, 13, 14. Sample 2 was less varied, 7, 10, 10, 10, 14. Sample 3 had no variation at all. They all have a mean of 10. So sometimes a measure of central tendency doesn't tell you everything. Sure, the average is all 10. So do I say all 3 samples are the same? No way. Okay? What we need here is some measure to say how much they varied. The mean is 10, but did it go down to noughts and 20s? Were they all 10s? The most simplest one, still useful, is just range. We would have done range before. It's just highest minus lowest. So like in this one, the range of this data, 14 minus 6, well, the range is 8. 14 minus 7, the range is 7. 10 minus 10, the range is 0. So it might not be the most sophisticated measure, but it clearly told me a lot about the third sample. Okay, there was no variation at all. Every answer was 10. So with range, all we've got to do is highest minus lowest. So the range of the following data sets, well, in part I, all I care about is the highest and lowest. I don't care about these middle dots. Highest there, lowest there. My range I don't quote as 6 minus 1. I don't say 6 to 1. The range is 5. Highest minus lowest. That's how I put my range. The data spread over 5 units. Same with the next one. I just want highest minus lowest. I've got to go fishing a bit. The highest quiz, the result closest to the outside of this radar chart, is this one. There's 8, there's 10. It's clearly the 9. The lowest mark, there's the 0, there's 1s, there's 2s. It touches 2. Yep. There's a range of 7 in that radar chart. The maximum was there. The minimum was at 2. 9 minus 2 is a range of 7. Okay. So range, simple as that. Standard deviation we've got to spend a little bit more time with. And fairly interested in just getting a concept so it's something a bit more meaningful. So it's the measure of the average spread around the mean. So here's an example I've come up with. Say I check the prices for a certain model of laptop. JB is selling it for $720. $730 at the Good Guys. Oh, out of date. $750 at Dick Smith. $760 at Domain. So everyone's quoting similar sort of prices, but not exactly the same. The average of these prices is $740. So the mean of this data is $740. But maybe I want to know how varied people were. I mean, no one quoted me 500, another quoted me 1,200. The variation wasn't massive. But how do I work out the variation? All the prices are 10 to 20 from the mean. Because 720 was 20 under the mean. 730 was 10 under the mean. 750 was plus 10 over the mean. 760 was 20 over the mean. So on average, the results were 10s and 20s for the mean, approximately $15. That's rough as guts, but I would say the standard deviation of these prices was something like $15. In other words, on average, people quoted me plus or minus $15 away from the mean. So it was very normal to them to be either $15 more expensive or $15 less. If someone said, I went for quotes on a laptop that averaged 740 and the standard deviation was 100, that's massive. That's saying it was really normal for people to quote $840 or $640. You know, unlikely. So when someone says a standard deviation is big or small, it depends on what you're measuring. If I had a standard deviation of $1 here, that would be tiny. That the suppliers only varied in about $1. Okay? But if we were saying for a product that only cost $5 and the standard deviation was $1, that's pretty big. It was only cost $5. Some of them were selling for $4 and some were selling for $6. So that's what standard deviation is, the average difference from the mean. So there's me saying all the scores. So the data in this experiment was 720, 730, 750, 760. X minus X bar. That thing just says get your score and take the mean away from it. Okay? This is a system to try and work out how big are our differences. And if I did that, that's what I scribbled on the last one. Since the mean was 740, if I go up to every score, what's that score minus the mean? 720 minus 740 is minus 20. 730 minus 740 is minus 10. 750 minus 740 is 10. And 760 minus 740 is 20. What we're creating here is we're finding the exact standard deviation. Now this might seem a bit stupid. The method of a standard deviation is, because we've got minuses in there, if I wanted to find the average of all these numbers, I would add them up and divide by 4. Minus 20 plus minus 10 plus 10 plus 20 is 0. 0 divided by 4 is 0. So I'm saying the average difference was 0. That's not right. The problem is caused by I've got positive numbers and negative numbers. The reason why this column exists is if we square negative numbers, they become positive. If we square positive numbers, they stay positive. So the only reason why this column exists is to turn all the numbers into positives. If I get minus 20 and times it by itself, I'll get a positive 400. Minus 10 times itself is 100. 10 squared is 100. 20 squared is 400. So the only reason I squared everything was to make everything positive. So I could find the average of these ones. If I add up all these numbers, I get 1,000. And there were 4 bits of data. So the variance, it's a word that we're not going to use much, but next year they will. If you get asked about the variance of data, it's exactly the average of the squared differences. Like, what's the average of these numbers? They all add up to 1,000, and 1,000 divided by 4 is 250. The variance of this data is 250. What's more useful to us is we squared everything. So that's the average squared distance. What if I just want to know the average difference? How do I undo that squared we did before? Square root it. The standard deviation is a square root of that number. So the standard deviation is root 250, which is 15.8. I said before the prices on average are about 10 or 20 away. So the standard deviation will be about 15. It's 15.8. Okay? This is a formula. This is the method that we're going to work out standard deviations. Next week we'll just chuck it in the calc, but not this week. Now that one could have seemed a bit full on, but we're going to, the last few minutes will just be spent making sense of what I'm talking about here. That formula I know looks horrible, but what that has said was the standard deviation, it's given this little thing which is a sigma. Ironically and annoyingly, that thing before that I said summed things, that's a sigma as well. This is an uppercase sigma, and this is a lowercase sigma in the Greek alphabet. So they're both called sigmas. We don't need to label that. I just know that this is our little symbol, and it's like, you'll see it, it's like that. I'm not good at drawing these things, but that's how they're doing them. That's our standard deviation symbol. And it's always, the standard deviation is a square root of the average of those squared numbers divided by n. So, if we get a large standard deviation, that means the numbers varied a lot. They were spread a lot. If we get a small standard deviation, they're all clustered. They're all really close to the mean. Here's another example before we just go to, I think I might have 3, where we just say this is what we do. Let's pretend these are the quiz marks for some made-up students. Someone got 6, someone got 3, someone got 8, 6, 5, blah, blah, blah. There's some random pretend quiz marks. Now, if I added all of those quiz marks up and divided by those 10 students, it tells me that the mean is 6. So there's all my quiz marks, and the mean of all those results is 6. If I now want to find the standard deviation, I know the standard deviation is going to be like, on average, they're maybe 2-ish above or below the mean. It wouldn't surprise me if the answer to this standard deviation was 2, but let's do it accurately. What really happened? How far was each score away from the mean? The first one was none away from the mean. The second one was 3 under the mean, 2 above the mean, 0 away from the mean. And so there I look at all those results. And all of that is exactly the same as doing that column. There's all my scores, and there's me when I've taken the mean away from all of them. So that was right on the mean, 3 under, 2 above, and so on. The next column we said was, I don't want these negatives, let's square everything. All right, there's my squared column. We got every number, 0 squared is 0, minus 3 squared is 9, negatives became plus, everything just got squared. And we said in that last slide that the average of all of these getting square rooted is our answer. Here's the formula. The standard deviation is equal to the square root of the sum of all of this column. The sum of this column is that number. How many scores did we have here? We had 10 scores. So the sum of all of them is the 44. There are 10 scores. 44 on 10 gets square rooted as 2.1. Hopefully that makes sense that the standard deviation of those numbers is around 2-ish, 2.1. That was really common to be 2 up or 2 down. So again, this is the same working out. Here's an exact example, written the same way you get presented, with heading titles and all of that. And this is going to be blank for many, but hopefully not for anyone in this room or watching Lectopia or Ecosystem, because it's very much the same, every single question. Find the standard deviation of the scores 1, 2, 3, 4, 10. Fine. 1, 2, 3, 4, 10 are all the scores I've got. The column heading here says, take the mean away. So I need to find the mean. All right? I'll find the mean of all my scores. The mean of my scores is equal to add them all up and divide by how many I've got. If I add all these numbers up, I've got 10, so that's 14, 15, 16, 17, 18, 19, 20. They sum to 20 and there's 5 of them. 20 divided by 5 is 4. So all this column says is take each score and take 4 away from it. 1 minus 4 is minus 3. 2 minus 4 is minus 2. 3 minus 4 is minus 1. 4 minus 4 is nothing. And 10 minus 4 is 6. So they're all my distances. The next column just says square everything you just got. Rightio. I know minuses are going to become pluses. Minus 2 squared are 9. Minus 2 squared are 4. Minus 1 times itself is a 1. 0 times itself. And 6 times itself. Okay. We're going to average them up. So first I need to sum them. 36 plus 0 plus 1 is 37. We've got a 41 plus 50. So my formula says that the sum of this column, which is 50, divided by how many scores did we have? 1, 2, 3, 4, 5. I could put it straight at the calc, but 50 on 5 is just 10. And root 10 is something. Root 10, it's about 3.16. I'll round it up. I'll call it 3.2 to 1 dp. So on average, these scores varied away from the mean by about 3. 3.2. I'm not sure what? Oh, wait, I'll leave it. Okay, so and here's another one. I think I've only got a couple, and it's the same thing. All right, if we were presented with this, could we do it? Yep. Can we find the mean of 4 scores? Yep. The mean of these scores, 5 plus 5 is 10, plus 9 plus 1 is 10, it's 20. This time it's 20 over only 4 scores. So my mean is 5. My column header just tells me now take the mean away from every score. In other words, take 5 away from every score. 1 take away 5 is minus 4. 5 take away 5 is 0. 5 take away 5 is 0. And 9 take away 5 is 4. Okay, square everything. I've got a 16, a 0, a 0, and a 16. This number is the sum of this column. 16 plus 0 plus 0 plus 16 is 32. This number is how many scores I've got, which is 4. So my standard deviation is the root of 32 over 4, which is the square root of 8, which is root 8, 2.82, blah, 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 2.8, just quoted to 1 dp. Okay? Yes, I can find a mean. Yes, I can subtract it from every score. Yes, I can square them all and add them up. There's no but coming. There's no, oh, but yeah, sometimes this happens. No, this is it. Okay. Given the concepts, we're not calculating anything here. Given the concepts, hopefully we've just discussed, do you reckon A, B, C or D, if say they were quotes in dollars for something, what do you reckon of those answers is closest to the standard deviation of them? Are they all about 10 off the mean? 150, 400, 2,500? At 150, I mean, the average is 2,500. So we've got something that's maybe 200 away, 100 away, 100, 200. The average of 100s and 200s, 150 is the only reasonable answer there. And some of our questions will be just that. It won't be calculated to say, which one makes sense? Exact answer 158.1. So yeah, it's pretty close. Now this is, okay, last one here is just a check. Well, has everything gone all right? There's more numbers here. Does it really change what we do? No, it's just annoying. I need a mean. Okay, my mean result, add them all up. We've got 16, 26, 30, and there's another 10, 40, divided by 1, 2, 3, 4, 5, 6, 7, 8. And I'll make sure the means are nice. We don't need to get all fancy with it. 40 on 8. Okay, all I've got to do is take 5 away from everything. 2 minus 5, 4 minus 5. The other saying 5 minus 5, 7 minus 5, and 9 minus 5. Yeah, I can take 5 off everything. Square everything. Yep. It's easy to accidentally start doubling things or do another thing, but just square them. If I add up that column, I've got 20, 21, 32. So again, remember that number is just the 32. That number is just the number of scores you got, which was 8. So my answer is the square root of 32 divided by 8. 4 eighths are 32. Let's not go to the calc on this one. It's a nice, precise answer. The square root of 4 is 2. The standard deviation of all those scores is on average they're about 2 away from the mean. And we're done. All right. Catch you later.